I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the groups theory from Algebra of MSc first semester first. In groups, we have studied some examples of some theorems about groups. In last lecture, I will study the first isomorphism theorem, second isomorphism theorem, third isomorphism theorem, the Aslam lemma, and so on. Now see here next one theorem. Let G be a group, and for any non-empty subset S of G, N of S is a subgroup of G. Further, for any subgroup H of G. Next, N of S is the largest subgroup of G in which H is normal. Next, if K is a subgroup of N of S, then H is normal subgroup of KH. For proof, we have define N of S is equal to X belongs to G, so that X inverse is equal to S as E inverse is equal to S. We get E belongs to N of S. Identity element belongs to normalizer. Let xy belongs to N of S. Therefore, X inverse Y, yes, X inverse Y inverse is equal to X inverse Y, yes, Y inverse X. Therefore, X inverse Y, yes, Y inverse X. And yes, here associativity Y inverse Y is equal to E S X X inverse S X, and this is nothing but yes. This shows that X inverse Y belongs to N of S whenever xy belongs to N of S. Therefore, N of S is a subgroup of G. N of S is a subgroup of G. It is given that we have to prove that for subgroup A multiply B inverse belongs to G. Therefore, X inverse Y belongs to N of S. Therefore, N of S is a subgroup of G. Let H be a subgroup of G. H is a subset of N of H. Therefore, H inverse is equal to H for any H belongs to H. Let H is a subgroup of K. H is a normal subgroup of K. Where K is any subgroup of G, then K inverse is equal to H for any K belongs to K. Therefore, K is a subset of N of H. Now, for any G belongs to N of H, we get G as G inverse is equal to H. This shows that H is a normal subgroup of N of H, and if H is a normal in K and K is a normal, some K is a subgroup of G, then K is a subset of N of H. Hence, N of H is the largest subgroup of G in which H is normal. Third part. For given it is given that K is a normal, K is a subgroup of N of H. Hence, for all K belongs to K, K inverse is equal to H. Hence Hk is equal to Kh. This shows that Hk is a subgroup of G. Therefore H is a normal in N of H and K is a subgroup of N of H, and therefore Hk is a normal in Hk is a subgroup of N of H. Therefore H is normal subgroup of N of H. Therefore H is normal subgroup of Kh. Therefore H is subgroup of Hk. Next theorem, let G be a group. H is a subgroup of G such that index of G over H is equal to 2. Then prove that H is a normal subgroup of G. For proof, suppose that G belongs to G such that G does not belong to H. Then G is equal to H union Hg and H intersection Hg is equal to 5. Similarly, G is equal to H union GH and H intersection GH is equal to 5. Hence, this is possible if and only if Hg is equal to GH. Thus, for any G does not belong to H, we get Hg is equal to GH. But as for any GH belongs to H, we have HH is equal to HH. It follows that Hg is equal to Gh for each G belongs to G. Therefore, H is normal subgroup of G. Next theorem. Let G be a group. Then the following statements are true. The set of conjugate class of G is the partition of G. Coordinate of class of conjugate of A is equal to index of G over N of A. And third one, if G is finite, then coordinate of G is equal to summation of coordinate of G over index of G over N of A. A is running over exactly one element from each conjugate class. Proof: define a relation equivalence on G by A equivalent B if and only if B is equal to X inverse. Then equivalence is an equivalence relation on G, and the equivalence class containing A is C of A. Hence G is equal to union of C of A, disjoint union. Hence C of A such that A belongs to G forms a partition of G. Now we have to prove that coordinate of C of A is equal to G over N of A. Let R denote the set of all right coset of N of A in G. Define a map F from C of A to R by F of G inverse is equal to N of A G. We go F is well defined, obviously true. Therefore, we have to prove that F is 1 let Nx is equal to Nay. Therefore, Nax is equal to Nay. That is xy inverse belongs to N of A. Therefore, xy inverse of inverse is equal to A. Xy inverse A is equal to Axy inverse. Therefore, y inverse Ax is equal to x inverse Ax. Therefore, f of x inverse Ax is equal to f of y inverse Ay. Therefore, x inverse Ax is equal to y inverse Ay. Therefore, f is 1. Now we have to prove that f is onto. Let G belongs to R, then for this G belongs to G. G inverse AG belongs to C of A, and f of G inverse AG is equal to NAG. This shows that f is onto. From first, second and third, we get there exists a mapping f from C of A to R, which is both 1, 1 and onto. Hence, coordinate of C of A is equal to coordinate of R. is equal to index of G over n of A. Next, third one, since G be a finite, that is, as G is equal to union of C of A over A, disjoint union, we get coordinate of G is equal to summation of coordinate of conjugate of A over A is equal to summation of index of G over n of A over A, where A runs over exactly one element from each other, each conjugate class. This is proof.